Well, it's a real pleasure to be here this morning and to describe TESS to you. This mission is one that we've worked on for many, many years. It's been the canonical 7 years of agony, and now comes the next 4 years of panic while we're getting ready for launch. The team that actually put this together is shown in this slide. This is a very accomplished group of both experimentalists, people who've had experience using small satellites in the past, as well as about a dozen participants from the Kepler mission, and so we're learning a great deal from the heritage of that mission as well. The partnership that is putting together TESS is shown in this slide. It's led by our group at MIT with participation by MIT's Lincoln Lab in many parts of the payload. Goddard is providing management. Orbital Sciences is providing our spacecraft, and there's also participation by NASA Ames for the pipeline, Harvard Smithsonian, and STSCI. I'd like to begin by doing a little bit of an imaginary experiment. And the imaginary experiment is assume for a moment that we've got some means of actually establishing a new Earth-sized planet every month. And what might that consist of? Well, we might find planets that are orbiting red stars, so-called M-dwarfs. These are the most common star in the solar neighborhood. About 3/4 of the stars that we know of are such M-dwarfs. There might be planets orbiting binary stars. More than half the stars in the solar neighborhood are also binaries. And then there's the likelihood that there would be many small planets of various types, some water worlds, some super-Earths, some Earth-sized planets. But this process of actually carrying out such an imagination is something that we're going to be able to turn into reality with TESS. And because this topic is of such general interest to the tax-paying public in the U.S. and as well as to professional astronomers, and this is something that has such broad applicability, we often refer to TESS as being the people's telescope in that sense. I'd like to now turn to defining exactly what is a transit. I think this is a concept that many people are familiar with, but it's interesting to see how much information you can observe and deduce from such a simple observation. If you have a planet orbiting a host star, and it just happens to turn out that the line of sight from us to that host star lines up approximately with the plane of that planet's orbit, and as the planet goes around, you get a dip in light when the planet goes in front of its host star. And from this information and the details of the ingress and the egress, you can actually deduce a great deal about the physics. To first order, you determine the diameter of the planet relative to its host star. But in addition, there's a great deal of additional information that you can learn from 3 other times in the light curve when this is actually taking place. At the time of the primary eclipse, when the planet is actually passing in front of its host, you measure the size of the planet directly. But moreover, if the planet has an atmosphere and the light is actually transmitting through this region that's shown in blue on the slide, the signature of the molecules and the atoms within that atmosphere can actually be deduced. So you can look for signatures that might perhaps even be indicative of biosignatures. Out of transit, you can learn about things like the meridional circulation, the temperature profiles, thermal phase curves. There's an enormous amount of information that can be deduced from that. And then finally, in the secondary eclipse, when the planet goes behind the host star, you can see the planet thermal radiation appear and disappear, and that means you can actually subtract out the effects that are actually due to the star itself. The science goals that we've established for TESS itself are shown in this next slide. And there's the cartoon in the upper left-hand corner gives a little bit more detail about what the transit profile will actually mean. The central goal of TESS is actually to determine transiting Earths and super-Earths that are around bright nearby stars. And that means we're focusing on rocky planets and water worlds. And what we really want to do is find a very good collection of what we refer to as the best planets. And this is best in the sense that they're the ones that we can look at readily in the future and make the most and determine the most information for the physics of the system that we have. Now, at present time, there's only 3 such systems that are known, despite all of the hundreds, thousands of planets that are now known, because these are the ones that are orbiting bright stars for which the full panoply of tools that astronomers would like to bring to bear are available. So the way TESS will do this, it'll carry out a large area survey of bright stars. These are stars of a variety of spectral classes. We're going to target all the M dwarfs that are known within about 60 parsecs, and we'll carry out an all-sky observation, both in which we look at previously known target stars, and there's about 200,000 of those, and this is done in what we clumsily refer to in English as postage stamp mode. The French term is much nicer, imagettes, and so that's what we'll actually do. And then in addition, we'll be able to bring down the full frames at a 30-minute cadence for about 20 million stars. Okay, well, the question that often comes up is TESS is following on from Kepler and Corot, and what is it that is new about what TESS will be able to do? Well, TESS is really, as I said before, addressing the question of where are the nearest rocky planets. Kepler was primarily targeting the question of how common are true Earth analogs. And by my saying that TESS stars are brighter than Kepler stars, how do we make sure that that's the case? Well, there are 2 ways. The first way is that we increase the solid angle by about a factor of 400, and that means the number of accessible bright stars in the sky increases by that same factor. And the second thing is that we select stars that are nearer by about a factor of 10. The Kepler stars are about 1,000 light years, and TESS stars are 10 times closer. So by 1 over r squared, that means that the TESS stars will indeed be about 100 times brighter on average. Now, we've done more careful simulations of this, and this is a plot of magnitude versus planet radius. The dots shown in blue are the Kepler stars, and the dots shown in red are what we expect for the TESS stars. So you can see that since it's a log scale effectively on the y-axis, that the TESS stars are in general about 100 times brighter, and that means that they'll be easier to follow up much more readily. So given that we're going to be able to do this, what are some other aspects of the images themselves? What this image actually shows is a small subset of one image from one CCD on TESS. This is about a little less than 10 square degrees, and this is the image that we would get by stacking 30 minutes worth of data, which is one of the data modes that TESS will have. So it's about 0.3% of the instantaneous TESS field of view. So on the scale of this image with the cameras that we have on TESS, the overall images would be about 20 stories high. And within these images, the limiting magnitudes are shown in this table, and as you can see, as we move down toward 14th magnitude, the number of stars grows to about 24th magnitude. So if you were to compare this to what is done with the imagettes, they would only cover about 2% of the field of view. So the remaining 98% would be a portion of the sky that we would not know anything about. So that's the real advantage of this mode, in that we will be able to provide full-frame images at the same 30-minute cadence that proved so successful with Kepler. The cameras are shown here, and after the previous talk, it's a little embarrassing to say how big these cameras are. These are the types of cameras that if I were in Boston, I'd say it was a Boston Bruins game that the photographers would be, but here, of course, it would be the Canadiens. And the properties of the lenses are such that the open aperture is about 100 millimeters, and the passband that we're covering is from 0.6 of a micron to 1 micron, and the number of cameras that we have altogether is 4 cameras, so it covers about 2,300 square degrees at every shot for the mission as a whole. And these are the timing parameters that we actually have. The basic frame time from the CCDs, which are also produced at MIT Lincoln Laboratory, is 2 seconds, and the other properties you can read from the frame. In preparing to have TESS flown as a NASA Explorer, we actually, in our Phase A, were able to produce 2 prototypes of these cameras. The first unit was used as a thermal demonstrator. The operating temperature of the system is minus 80 degrees, and so we had to make sure that it would stay in focus at that level. And then we built another unit that we could actually vibrate to the levels that would be required for launch. This is the size of the camera that you can see. This was taken shortly before Christmas, and we had our local Santa Claus holding it to us. And it weighs about 10 kilograms, and the person actually holding it was the project manager at NASA Goddard. And then we also, as part of the preparation for presenting TESS in its selection process, we built a full-size replica. This is shown with 3 of the co-investigators on TESS, Sarah Seeger, Josh Wynn, and Roland Vanderspeck. And the image that you see, the part that's in silver is the spacecraft itself, which is an Orbital Sciences Leostar 2 750. There's a K-band dish that's shown in the lower left next to Sarah. And then the upper part in gold is where the 4 cameras actually reside. This diagram shows the way the fields of view of the cameras are actually arranged. TESS looks anti-sun, and when it is looking anti-sun, the 4 cameras are arranged as you would display your hand, with the topmost camera looking at the ecliptic pole, and the other cameras being juxtaposed as you move down toward the ecliptic itself. Now, I'd like to show a short video that gives you the sky mapping strategy. This is a video that's on YouTube, so there's a lot more information there if you choose to look at it. So this actually shows TESS in orbit, and the fields of view of the cameras are actually shown extending from the ecliptic up to the ecliptic pole. Each is 24 degrees by 24 degrees, and they're edge-abutted as you move up in ecliptic latitude. We observe with a stair and step mode, where we actually move every 27 days to a new field. And so we're basically pivoting about the axis of the ecliptic, and so we remain fixed in inertial space for these 27 days. And in this way, we actually cover one hemisphere in a lunar year of basically 13 orbits of the satellite. And then we flip the satellite around and then go to the southern hemisphere in our baseline mission. And noting that we cover the continuous viewing zone for JWST very efficiently by this mode. After the 2-year survey, we end up with this sky coverage map, and the color code indicates how many days of observations there are for each of the patches of the sky. And the area that's shown with the dashed line at the pole is the JWST continuous viewing zone. So there's altogether about 900 square degrees of sky for which the observation period exceeds 300 days. Now, one of the key things that were able to achieve in doing TESS was to arrange for an orbit that would provide the coverage that we needed without having the problems that one has in low Earth orbit, which is normally where small explorers from NASA actually fly, or explorers in general. So this video shows the mission orbit insertion into that special orbit which we utilized. The rocket launches first into this highly eccentric orbit with an apogee of 250,000 kilometers, and then we gradually raise the transfer orbit perigee until after 3 such iterations, it is approximately at the distance of the moon. And then the phasing is arranged such that when TESS actually reaches the moon on this final, or the moon's distance at this final orbit, it does a lunar flyby, and it comes within about 2 lunar radii, and there's a large deflection that occurs, which actually changes the inclination to about 37 degrees. And then there's a period in which it moves out, and then it comes back to the Earth. And then there's an orbit adjust maneuver that actually puts us into our final trajectory, which has a radius of 17 Earth radii and an apogee of 59 Earth radii. And in this way, we actually achieve something that's really important to the mission. And the way to think about this is we're in a 2-to-1 resonance with the moon. And the importance of this is that it provides us a place where we come close to the Earth so we can use high data rates, but it also stabilizes the orbit itself, because for 2 weeks in the lunar month, the moon is torquing on the orbit in one direction, and then the other 2 weeks it's torquing in the other direction. So we basically end up being able to stabilize the orbit in a secular sense, and we thereby end up with an orbit that's actually stable without station keeping being required for the order of decades to perhaps as long as a century. So this is a really key part of the mission, and it took a great deal of work to actually find this orbit. This orbit enables and simplifies TESS in the 9 ways that I've shown in this slide, and the one that I'd really like to focus on is the high data rate one. The others are important, and you can read them, but the high data rate means that compared to missions that operate at Earth-Sun L2 or in the Kepler orbit, we have an enormous advantage in terms of the data rate that we can bring down, because our perigee is about 100,000 kilometers. The 1.5 million kilometers of L2, the square of that is 200, and that's a very big factor that allows us to bring down 200 gigabytes in 3 hours at perigee. So the science question that's often asked is, well, why do we need TESS now, and what are the implications that it has? This is a plot that actually shows the radius of the known planets as of last year compared to the orbital period. And as you can see, there are 3 that are shown that are sub-Neptune or smaller in radius. When you put the TESS planets on this, you can see the picture changes quite dramatically, and that's the reason why we're so excited about doing the mission on as soon a time scale as we possibly can. Now, it's not going to be sufficient to just measure the diameter of the planets, because the diameter, assuming the planets are spherical, will give you the volume, but you also need to find the mass, and with the mass and the volume you can determine with the mass and the volume you can determine the density, and that's of course what you really need to establish the nature of the planet that you actually have. So the flow down for validating these planets and making these mass measurements is shown in this funnel diagram. And the assets that are shown on the left are the ones that are actually fully committed to supporting the TESS mission as things currently stand. And as you can see, we start with the light curves from the 200,000 stars for which we have postage stamps, and we work our way down through this, eliminating false positives carrying out reconnaissance spectroscopy, and then the precision Doppler spectroscopy with the HARPS telescopes that are committed, and finally we end up with the measured masses of 50. Now this is the level 1 requirement that we have for TESS. Now in addition to these resources, the amount of data that this would represent is probably only of order 10% of the full wealth that will actually come from TESS. And so one of the things that we do is we deliver all of the data to the massed archive at STSCI in 4 months' time, so it's available to the community as a whole. And so what we expect is that the TESS masses will generally come in the whole from, at least to a larger degree than what the baseline mission will call, from the next generation of precision radio velocity spectrographs. And for low-mass red dwarfs, there's about 10 of these that are currently in progress, and you've heard about a number of these in the papers that have been given at this conference itself. So this is going to be something that I think we can all look forward to, the ways in which TESS will actually be complemented by this great number of new resources. Well, the topic I'd like to sort of close with is related to the habitable zone and how TESS will actually relate to that. This is a plot that was put together by Sarah Seeger that shows the mass on the y-axis relative to the Sun and the radii of the orbit relative to Earth. And the color bands that are shown going diagonally from lower left to upper right are what you expect for a number of models for the effects of greenhouse gases of various sorts. The light blue band is what you would expect from the traditional way of looking at the Earth and assuming that CO2 is a dominant greenhouse gas, and then looking at the water line as you move outward. But there are other ways to expand this habitable zone that are undergoing a lot of theoretical study currently. You can push, if you reduce the amount of water vapor that the atmosphere has, so that you're effectively dealing with a desert planet, but still 1 or 2% water, then you get the yellow band. And if you push outward, if you've got hydrogen to any degree in the atmosphere, that's a very powerful greenhouse gas, and so you can push things out correspondingly. The portion of this band that TESS will actually explore for habitable zones is shown in this red mark. And as you can see, it covers the habitable zone and for Earth-like planets as well as those that would be appropriate for this class of dry terrestrial planets. To see this a little bit more quantitatively, this plot shows the stellar temperature along the y-axis and the insolation ratio, that is the fluence that you have from the host star compared to that of the Sun along the x-axis. And this is for planets that are less than 2 RE from the simulations. And so there are 3 models that are shown here. The one that I've highlighted in yellow is one by Tsom et al. And then you can see from the number of crosses that are shown that the bulk of the TESS habitable zone planets will be M stars or late K stars. And there's about 20 or so that we can expect from these simulations. Well, one thing that's interesting to do is to write the results that we think we will be able to achieve for TESS operating with JWST in sort of a Drake equation of sorts. This is not really the classical Drake equation, but it's really, the number of planets that you can have detectable biosignature gases for. And I've listed the factors in the table below this, and if you actually plug in the numbers that we expect from TESS, it's actually quite promising in terms of what we will actually see. The expected number for such M dwarfs might be as of order half a dozen. So that's one of the things that we're excited to look forward to. The legacy that I think we can expect from TESS is indicated in this. The launch is in 2017, and at that time we'll be able to identify the best and smallest targets, and this should be just in time for JWST and the coming generation of extremely large telescopes that we've heard quite a bit about at this session. And then, of course, future probes and large missions that will come in the following decades. So I'd like to finish by summarizing a number of points. TESS is going to be an all-sky survey. The launches will be in 2017. The cadences, there are two primary ones that I've discussed, and the observation scenario is as shown in the lower portion of the table. We'll cover almost the whole sky in 27-day cadences or observation periods, and the period for which we would be able to look for habitable zones around a variety of small stars is 80 days, and then the sweet spot for JWST will cover about 900 square degrees for greater than 30 days. And then finally, this is a summary of the expected TESS yields, and then tomorrow I'll talk a little bit more about some of this material in somewhat more detail. One of the topics, and there's also a poster that Peter Sullivan prepared for the meeting that shows a bit more of experimental details about the testing that we've done for the cameras, and the fact that the two topics I didn't really talk about were giant planets, and there's a very large number of those that we should be able to detect as well. Thank you.